Okay, so let's discuss this magnifying glass thing. So magnifying glass, the way it works is this. Let's say your eye. So magnifying glass. The magnifier, right? So without the aid of a so this writing, for example, is too far away from you, right? So it looks small. So it looks small because just like for me, I mean, like even like that wall, which is like 8 feet, it looks this big from here, right? Because that's the angular the angular distance. It looks just this big. But if I get closer, it will look bigger. Okay? So here's the eye, the person's eye. This is the lens for the eye, and this is the retina. This is the retina. Let me. I will first draw an object here. By the way, every angle I draw is all things I'm drawing is exaggerated. The angles, they look big, but they're actually smaller. So this object here, this in white chalk here, it's going to be to occupy a certain angle in our retina. It's going to be like basically this big. That's the angular distance. So it's going to occupy this angle in our retina. And at the end, it's just this much. Okay? Is that clear? So we'll see it that big. If I bring this object closer, same object. The object itself did not get bigger, right? The object itself did not get like bigger. So let's make the same object, well, let's make it closer. Here's the same object, but now it's closer. Let's see how much it will occupy. So it will occupy this much in our eye. Okay, occupy this much. So it will appear bigger, just because we brought it closer. Here's the problem though. Can we bring it this close? We can't. You cannot just bring it this close. There is a limit to how close you can get it, and that's called the near point for the eye. You can only bring it this close, and this close is just called N, the near point for the eye. How much is the near point for the eye? Depends on the person. On average, like for a lot of people, I should say, in the book they say just 25 centimeters. Again, not everybody is 25 centimeters. Probably it's maybe 25, 30 for me, maybe 20, 25 for you. The younger you are, the more, like if you're a 5-year-old, it's like maybe 5, 6 centimeters. So this near point changes with age. So I just call it N. Okay, that's the near point. And so the object itself will have a height Y. So the angle here, let me call it theta. That angle, this angle, maybe in red, theta is approximate. If theta is small, then y over n is equal to theta. Y over n is equal to theta. Right? You see that? If the angle is small, y over n is the tangent of theta, and tangent is almost sine, and sine is almost theta. Right? It's a small angle. But theta here is in radians, of course. Right? Is that clear? All right, sounds good. So now, here's how magnifying glass works. You get the eye. Here's the eye. Here's the eye lens. And then we put some convex lens in front of it, converging lens. That converging lens will have a certain focal length. Typically, the focal length of the lens, of this lens, will be smaller than the near point of the eye. So F is less than N. Okay? F is less than N. So let me put my object right here. That same object right here. And it is Y. And then now the angle it will have is this angle. And this is, let's call it theta prime. Okay? Theta prime. So what's theta prime? Theta prime will be y over f, isn't it? It's y over f. By the way, the image will be somewhere here. It will be a virtual image. It'll be somewhere there. I don't really care about the image because the angle is still going to be the same. It's the same angle. So I have y over f, that's theta prime. So how much bigger is this new theta compared to theta without the glass, without the magnifier? Well, the magnification then, m, okay, let me call it m0, m0, is equal to this. It's equal to theta prime divided by the angle without the glass. This is an angular magnification, notice. It's not that the object itself became like this big. It's just because we brought it closer, okay? Is that clear? All right. So theta over theta prime, let's see what we get. Theta prime is y over f, and then divided by theta prime over theta. What's theta? Y over n. So y over n. Well, if you divide, you're multiplying by the reciprocal. Sorry, let's just do it in one. So you're multiplying by the reciprocal. So this is the height of the object, cancels. So the magnification, I'll call it here m0, is going to be just the n over f. N over f. Your near point divided by the focal length of this magnifying glass. Okay. So, for example, and you will notice that the smaller the f, the smaller the focal length, the bigger the magnification. Wouldn't you agree? Right? If f is small, you get a larger magnification. And this is f equal to positive 100. And let me give it to you so you can just take a look at your hand. You can just kind of. Technically, I should be looking really close. The glass should be on my eye. So just try to move your hand and then see when it is. I'll start with you. You can pass it around if you want. I have a 250, a 200 millimeter lens, but 200 millimeters is almost equal to n, right? 200 millimeters, 20 centimeters. So they're close. But the 100 is, you can look, it's bigger. So you can look at your hand and then, yeah. So and then just pass it around. Okay. So that's it. This is the magnification. So that's how magnifying glass works. And then, is there a maximum magnification? Or maybe I should skip that one part, and then I might come back to it, assuming I have time. Yeah, I will maybe. Yeah, let's do it. Let's do it. Let me be thorough and actually do it. I was going to skip it, go to the microscope. Let's be thorough. So you might ask, why stop at the focal? Yeah, why stop at the focal point, right? Why not bring the object closer? At some point you will not be able to see it because you see here, if it's at the focal length or near the focal length, the object will be far away. The image will be far away. The problem is, if I bring it too close, the image will form somewhere here, and if that somewhere there is more than closer than the near point, then I will not be able to see it. So meaning, here's what I mean. So here is the eye. This is the eye. This is the lens, and this is f. This is the focal point. I might, if I bring the object somewhere here, the angle will certainly be larger. This is, let me call it now theta double prime, right? Theta double prime. And the image will form somewhere here, somewhere there, right? Will form somewhere there. The problem is, if this somewhere is nearer than the near point, then it would be blurry. So the maximum distance I can bring it in is when the image is at the near point here. Does that make sense? When the image is at the near point. So let me ask you, if this is the object and this is the image, they're on the same side of the lens. Is this image real or virtual? The image, it's virtual. The image and the object are on the same side, so it's a virtual image. So this distance, this way, this is the S prime, is going to equal to, it will be some negative number. It will be some negative number. And how much is it? The maximum it can be is the near point, which is n. Okay, how much is it? It's equal to the near point, which is n. Okay. Now, how big is this? Let me call this one here y prime, and this is y. Okay, this is y. Okay. Yeah, as you're looking at the magnifying glass, did you see? Isn't it interesting? Right? Yeah. I can give you the 250 lens, but you can play with it next week in the lab, and then you can see the magnification for yourself. You want f to be smaller. So now let's figure out what this theta double prime is. What theta double prime is. So we know this is s, right? This is s. So I know 1 over s plus 1 over s prime is equal to 1 over f, and therefore 1 over s is equal to 1 over s prime. No, it's going to be 1 over f minus 1 over s prime, isn't it? Minus 1 over s prime. Yeah, 1 over s prime. This is, yeah, I think, yeah, that's okay. Then what is this angle here? Theta double prime is going to be y prime, right? Y prime divided by this distance, which is what? Negative n? It's going to be divided by n. Divided by n. N is just the length. S prime is negative because it's a virtual image. So so what's this one here? The magnification is going to be minus s prime over s, which is going to be minus, minus s prime over s, minus s prime, that's just n, isn't it? Yeah. Negative s prime is just n. So n times 1 over s. What is 1 over s? 1 over s is equal to 1 over f minus 1 over s prime. 1 over f minus 1 over s prime. 1 over s prime. But what is 1 over s prime? I'm just substituting. Negative 1 over n, right? So I'm going to put minus n here, right? But I have a minus minus, so it becomes a plus, doesn't it? So it becomes just n and then a plus. Okay? That's the magnification. Yeah, so that's the magnification. Then what's the height of that object, y prime? Y prime would just be y times m, right? Y times m. And so it's going to be y. So it's going to be y times m. The magnification is going to be n times 1 over f plus 1 over n. Okay. Now the angle theta double prime, so theta double prime will equal to y prime. Right? It's going to be this distance over this distance. So that's y over n, y prime over n. Y prime over n. So let's do it. So what is y prime over n? Y without the n, right? This is this. So it's going to be y times 1 over f plus 1 over n. Okay. Finally, the magnification, the new magnification. This one I called m naught. This one here I'm going to call maybe m1. Is going to be theta double prime divided by without the glass. So it's going to be this y 1 over f plus 1 over n times, what is 1 over theta? Theta is y over n, so it'll be n over y. Okay. It's going to be n divided by y. I probably did it the long way, but that's okay. The y cancels. Now take the n inside, so you get this. M1 will equal to what? N over f plus 1, yeah. What is n over f? That's this. That's m naught. So this is equal to just m naught plus mu. Okay. Whatever the magnification is, if you put it at the focal point, if you bring it any closer, you will just have an increase of 1 in magnification. The problem with that is, one, if the magnification, let's say, if m naught is 20 and then it becomes 21, yeah, it's an increase, but it's not that much. And it's not worth it in a way, because if you bring it closer, the image will be at the near point, so you can barely see it. Your eye is stressed at that point. Whereas if you just let it at the focal length, the eye will not be stressed. Okay, that's it. Quickly, for a microscope. How does a microscope work? A microscope uses 2 lenses. Okay, so I will orient the microscope kind of vertical. So you have the first lens here, and you'll have the second lens here, and then you have the eye. This is the person's eye. Person looking. It's not a light. The eye. The eye. Okay. This is called the eyepiece because it's the one next to the eye. Eyepiece. And this one is the objective, or the object. Yeah, the objective. Objective. This lens is called the objective. This one is the eyepiece. This one is the one near the eye. This one is near the object. So let's say you want to view. So this lens here will have a certain focal length. Let's call it. This is f1 for the eye, for the objective. The focal length of the objective. And what you do is, in a microscope, right? You can adjust it. You can move it up, down, and then whatever you're trying to view will be somewhere here. So the thing that you're trying to view, maybe bacteria or whatever, something small, is going to be here. So if it's beyond the focal length, if it's just beyond the focal length, this is the object distance. This is s. There will be an image. That image will be what? Is it going to be real or virtual? If it's beyond. If it were here, it will be virtual. But it's a little beyond. It's actually going to be a real image. It's going to form right here. Right? Remember, if it's beyond the focal point, it's going to be real. So the image is going to form somewhere here. There will be an image somewhere here. And somewhere there is designed, it will coincide with the focal length of this. So what happens is, this one is really close, so it will create an image here. And that image will be magnified. And then it's already a magnified image, and you're viewing it with magnifying glass. So the distance from here to this image is going to be approximately equal to the focal length of this lens, of the objective piece. So you're magnifying and then magnifying yet again, so you're multiplying by 2 factors. And so the magnification could be 100, 500 times, something like that. So that's a microscope. So microscope, you're viewing a nearby object that is too small. Okay? Because you can't just bring it arbitrarily close to your eye. You can only focus at the near point. So that's what the microscope does. Telescope, what does it do? Do you view close by objects or far away? They're far away and big. Yeah, they're big, but they're far away. You can't see them with your eye. So a microscope works, a telescope works like this. So now let's say, I'm going to orient them horizontally. So we're here, here's our eye. And there will be, again, an eyepiece and an objective. Okay? An objective, this one, and an eyepiece. Okay. Now, from here, the objects you're viewing are very far away. If they're very far away, what is s? The distance. Infinity. So you have 1 over s, which is b0, 1 over s plus 1 over s prime. So 1 over s prime is equal to 1 over f. So the image will form somewhere here. The image will form somewhere here. Right? Because you have this, 1 over s plus 1 over s prime is equal to 1 over f1. Let's call this one here f1. This is the objective. So this one is 0 because it's a really large distance. So the image is just going to be somewhere here. The image is going to be somewhere here. It's going to be a real image, right? Who can tell me why it's real?
The same size as the object.
Not quite. The distance. Why is it real?
It's beyond the focal point.
Because it's beyond the focal point. Yeah, the object is way out there, so it's definitely beyond the focal point. So the image is going to be formed at the focal point of this one. And guess what? This image would be small, but that's what this lens is there to do, to magnify it. And then we can view a bigger object. So this is the distance, right? It focused it at f1, and then this one, the distance from here to here is f2. And so the size of the telescope is just the sum of the two focal lengths, basically. Because you have a lens here and another lens here, and the distance between them is just f1 plus f2, approximately. Okay. You can derive an equation for the magnification, so on and so on. Yeah.
So the image is behind the focal point f1 or away from this f1?
So the image will just be basically at f1.
F1.
Because if it's at infinity, S prime will be equal to f1. Okay. Will be essentially at f1. Any questions on this? Okay. I mean, there are formulas I can give you for the magnification and so on, but I don't want to go on with this. I think it's too much probably. The author goes on and on and on and on. And there are cameras also that I didn't discuss. It goes on with the eye, the human eye. I think it's a little too big of a chapter, and then I would like to put an end to it today. Okay. Does anyone have any questions on these? Or as far as exams and so on, I will. Let me pause this.